this is not a pull-out test. This is a three-bending test. But still, the fiber works in a tension. So you can see that by comparing this picture with this one, you can see that it's more quantity of material that is attached to the fiber in presence of the embossments. And this is true also in the case of you create like a micro pull-out effects, and you have a macro pull-out effects and the micro pull-out effects as when the fiber is in place. And this is in grayscale, and probably the grayscale will give you a more. In the case of the titanium alloy, you will see also some mortar attached to the fiber, also without embossments. But because the 3D printed material has some roughness, some basic roughness due to the 3D printing process, so it's not completely smooth. So it offers some roughness as for granted because of the 3D printed process. And also I have also another study that we did after this, which is on the surface roughness. No, I don't want. I want to hear this bit. It's better if I use this one. I like it more. Okay, this is the other work that we published. This was only. This is about the titanium fibers. And we better investigated with electric microscopy, with the more refined microscopy techniques. We investigated the nature of the fiber before and after testing. And so those are T, S, and R. The S and R pictures refer to the smooth and the rough. S stands for smooth without macroscopic embossments, and R stands for rough. And you can see those are the embossments. And those are the SEM photographs before and after pull-out of the fibers from the matrix. And this is the TS and this is the TR. And there is more material attached to the, so there is this pull-out effect, as you can see in different ways. Actually, maybe we can do with Professor Singh another experiment that we would like to show the effectiveness of this fractal reinforcement. We could test composite material made of a transparent matrix, and we insert a fiber with some microstructure on the lateral surface, and we record the testing, and we can actually visualize the effect of the fractal reinforcement. That I should give you some homeworks. So the homework that I have is pretty easy and nice, maybe, is to build yourself a Koch curve. You can build a Koch curve with a given complexity. But for For that, let's first okay, there are several tutorials. So let's say that this is an equilateral triangle. Each side we divide in 3 equal sections. You see? I don't know if you can see properly. Divide in 3 sections. And then in the middle, you remove the middle section and you put another triangle, equilateral triangle, with the same side of the section. And so this is the first step. And this looks like the Star of David, the Israel flag. And then we keep doing this. So this is standard. What we have done is to do this, to propose this both for the cross section of the fibers and for the longitudinal profile. So this is the snowflake. It is a natural shape that resembles. There is the snowflake shape that resembles the cock curve, or the cock curve replicates the snowflake, as you prefer. So in my project, what I did is to use three complexity parameters. One related to the cross section that works like the one that we have seen, and the other two that are related to the longitudinal profile. So if I want to yes, the assignment would be to build yourself one of those shapes. Okay, so this is by using the cock curve always, so the construction, the easy construction that you have seen, you can build an object that is what did I do? Yes. So basically, this is the idea. This is the cross section that is attached to this profile, longitudinal profile. And so you can build yourself one object like this with these three recursivity, three complexity parameters, N, M, and P. And you will create something like this. Obviously, this you can change whatever you want, because you don't need, this does not need to be equilateral. It's just in the cock curve equilateral, but you can change the aspect ratio. If you want a fiber that has that is not whose thickness is if you want to create a microstructure that is more fine than the one corresponding to this equilibrium, you can take a triangle with a more smaller height, and then apply the construction with some refinements. But this could be an assignment that I could give to you. I don't know if I need to give you an assignment you have to do while you are here, this assignment. I'm not sure if you not that strict that you have really to do it, but if you want to do it, we can do it together. This is one first thing. The second thing would be to show the drawings. What? Yeah, yes, you can use the triangle, otherwise, but it can be done with other initial shapes. It doesn't need to be a triangle, but the triangle is one of the shapes, but you can start with an hexagon, you can start with other shapes. And you can do that also with other shapes. Chissà se si mette... Tu c'hai pure bisogno di un adattatore, c'hai l'adattatore? Innanzitutto prendi la serie. Prendi una serie, sono tante. Sono qui una serie. Vabbè, can show adesso. Mentre tu fai vedere questa, ne cerco un altro. Dove sta? Ah. Dove? Però io non c'ho il software. Non c'ho il software, ragazzi. Software. Non ce l'ho, penso. Quindi penso che devi far vedere con la tua. Startup. Sì? Okay, those are the. Yeah, you showed me you asked me about those are the drawings that we sent to the 3D printer. This was the idea of the transparent specimen to test under bending or tension to show the effect. Oh. Yes, you are not seeing anything actually. You are seeing that. Why that? Because I have to put this down. No, loro vedevano una cosa diversa. So why don't I see again? I need a render. Why I'm not seeing I'm not projecting. What is the presentation? What's wrong with that? There's something wrong? Oh no. It's not projecting anymore. No? You can use my... Yeah, okay. So those are the drawings of the fibers that we sent to the printer. Actually, I wanted to show you. Was also the idea. This was the idea of the specimen with the. Actually, you can theoretically 3D everything. Ora dopo vediamo. So she will show you the drawing, the CAD drawing, and I'm showing you this idea of 3D printing both the matrix and the fibers, the reinforcements. You can theoretically do both. If you have a printer handling two materials and with the right resolution, you can 3D print the matrix and the reinforcement and test the effectiveness. Maybe if you use a transparent matrix, you can test the effectiveness of the reinforcement of the interfacial bond, the increase of the interfacial bond during testing. These are fabrics obtained by using, this is with not triangular, but this is an hexagonal base cock curve that you can also use. You can use different polygons as a base, not necessarily a triangle. This is the fiber with embossment, just an initial drawing of the fiber with embossment. And now, I don't know if we have, those are the STL files that I probably don't see because I don't have Rely. I think we have to switch to Ilenia that has the software but you have to try something very difficult because the new Asus not always work, but the Mac very rarely work with the beamers. So we are trying the impossible. We are trying to switch to a Mac. And this won't work most probably, but we can try. This won't work.
No.
There's no possibility.
USB port that has HDMI.
No, I mean, but this has, do we have the adapter for this? No. Okay, no. So, okay, she can show you by showing by pass, yeah. We can show you at the table, yes. Yeah, that was too much. That was too much. I can do that. Thank you. First of all, I would like to switch time because it's 9:39 in Italy. You know that it's 9:39 in Italy now. But ok, come si cambia il tempo? Non mi ricordo. E poi? Qua? Non c'è niente. Ok, anyway, it doesn't matter. It doesn't matter. So, I want to check the time. Riconoscimento. Automaticamente. Okay, so now we have the right time, which is 14:10. She will show you. Those are very heavy files, and actually, this is a challenge to really test the fine scale fibers. Is a challenge. It's a challenge both if you want to 3D print the fibers, because the resolution of the printer is limited. You cannot go down fraction of millimeters theoretically, and second, also with the finite element simulations, you will find issues because you know that the scale of your discretization must be smaller than the smallest feature. So if you have the smallest size of your subdivision is the order of I don't know, of fractions of millimeters, that should be the mesh size. So you need at least around in a strip around the boundary of the reinforcement. But you can do some. You can simulate. If you want to do simulations, which could be another assignment, but just for her, because it's very. If you are not an expert, it won't work. You can simulate. You can do a finite element simulation of a fiber into a matrix, and you can simulate the pull-out test. And so, if you have a limited, you can either apply, I don't know, periodic boundary conditions so that you model just a section of the fiber, and in that case you can, I don't know, you have to use interface laws that are appropriate, friction laws, you have to use some interface laws to simulate to the interface, yes, for the interface. So it's also, that is a challenge. But this is possible, it's doable with some work, with some research work. It's theoretically possible, so you can add some friction law at the interface, and so you can, that would be sufficient. And with some cohesion, some angle of friction, and you can see the results. This is about the fiber, and one assignment could be to generate one of those fibers yourself, just to have some, also have some fun and see how it works. You might want to try with the hexagonal Koch curve, for example. It's not connected. Okay, this is an assignment to students. But those are just images. Those are nature shapes that replicate fractal shape. For example, also the lungs, the human lungs, have a fractal shape. You know, the bronchus. Yeah. That's the reason is the same as the increase of the adhesion, the bond strength in a composite material, because if you increase the lateral surface, you have a reduced space, but you have a lot of surface, so you can breathe more accurately, more effectively, because you have a large surface in a reduced space, just because of the use of this complex geometry. This is the same principle that we are investigating. And we were stuck for technical issues, because we were not able to go very, very fine, because it's a matter of resolution, really, the effectiveness of the approach. If you want to go down to the nanoscale or the micron scale, you need a printer, you need maybe you need a testing machine which is equipped with a scanning microscope for visualizing the effects of the fractal shape of the interface on the interfacial bonding mechanism. But apart from this assignment, that is about designing a fractal shape. I have a lecture that I am missing actually this morning. So, since I think that we have time, yes, 3:30 is the time we have to leave. I actually would like to show you this picture because it's something completely different, but it's something that may be nice to tell you, and maybe with some of you, as I saw before, we can explore maybe through assignments or future collaborations some possible future directions of given research topics. So the first lecture was about the general goal of my research over the last years is about these metamaterials. So materials that are have special properties which derive essentially from their geometry, more than the chemical nature of the material. So my research has been focused on the design by computation, through computational methods, of materials that have that are made in laboratories and have desired properties arising from the geometry of the structure of the material itself. So this other work is about, this other presentation was about a different, completely different material application. Is about a lattice structure that has some special properties, and the manufacturing, the additive manufacturing of such structures. So, in this case, I want to investigate lattice metamaterial. When I say actually there is a group behind all those projects. There are my PhD students and also external collaborations with this was, for example, with the University of California, San Diego, and the goal was to investigate on lattice metamaterials. So engineered lattices that have special properties deriving from the geometry of the microstructure rather than the chemical composition of the material. So the particular structures that I was investigating, I have been investigating, are those pentamode lattices. Pentamode lattices, actually with these metamaterials, you can obtain a class of extremal materials by playing with geometry. You can obtain some extremal behaviors, and you can obtain the so-called N-mode materials. N-mode materials refers to materials which have N soft modes, and the remaining one, while the remaining ones are stiff modes. Soft modes, for soft modes, I refer to, I mean modes with zero stiffness. So they have 5 given modes of deformation which are without stiffness, without any stiffness, theoretically. So our materials that basically do not react to some deformation. You don't need to apply any stress to deform the material in a given number of modes. And so there are B modes, 3 modes, 4 modes, and the weakest case is the 5 modes or pentamode material. Pentamode material is the material is a material, artificial material made in a laboratory that can deform without stiffness in 5 modes, and has only one stiff mode. In this case, the stiff mode is the volumetric, the stiff mode is the volumetric compression or expansion. So if you compress or expand spherically, in a uniform way the material, it will oppose a considerable stiffness. While in all the other modes of deformation, to all the other modes of deformation, the material will oppose 0 stiffness. If you pull in one direction, in another direction, if you shear the material, it will oppose 0 stiffness. How do you get this material? So why do I need such weak material, for example? No? Usually engineers need strong materials. But in some cases, you may need a soft material. For example, if you want to isolate a body from mechanical waves, you can envelope, you can wrap a body with this metamaterial, and due to the fact that 0 stiffness, you will isolate the material from mechanical vibrations. And this is what is called acoustic cloaking. Acoustic cloaking is one of the applications of these materials. Another application that we developed was about new devices for seismic isolation. So in seismic isolation, you want a material that has very low shear stiffness, because a building has to oscillate independently from the ground. So it has the device that separates the building from the ground needs to be very soft in shear, theoretically 0 stiffness in shear, but needs to be strong in compression. And so the standard, the pentamode material will not be effective, because to uniaxial compression it will offer 0 rigidity. And so we produced a variant of the pentamode that I will describe in short. But let's first introduce the general pentamode materials. How do you get to a pentamode material? It's pretty easy if you have a 3D printer, and if you have a computer. You produce a lattice structure that has like a diamond, which is shaped like a diamond, and has only 4 linkages concurring at the generic node, not more than 4. Actually, 4 is the minimum number of connections that you need to have in a node for a 3D structure to be stable. Otherwise, it will collapse. But if you insert the minimum number of linkages that are sufficient to give self-stability, freestanding configuration of the structure, you will get a pentamode structure. So this is the pentamode structure. And these are physical models. This is a physical model that has been built with some 3D printers that handle very low resolution. These are optical lithography. Through optical lithography, you can build a structure like this. Usually it's made of struts that have the 2 extremities that are bicones, and they are thick at the center, thin at the junction. Because for this structure to behave like a pentamode, so to have 5 soft modes, you need to have the junction that are theoretical points, because you don't want bending moments. If you have bending moments, if you have, you won't have, you destroy the pentamode, you vary, you don't reproduce the real theoretical pentamode behavior. So what they have done, they have tapered the struts towards the connection, the joints, in order to have some hinges, some nodes that do not transmit relevant bending moments. And the applications of those materials, this is a sample that's been built with a nanoscribe. I don't know if you know nanoscribe. It's a printer that works at the nanoscale. This is like a finger, this sample. And the main application available in the literature was about acoustic cloaking. So if you cover a body with this lattice in a different arrangements over the thickness, you can completely isolate a body which stands on this side of the lattice from mechanical vibrations. You can isolate from sonar, you can make a body invisible to vibrations. And so this is something that is useful also for military applications, as you can imagine. And but our goal was to apply such structure. So those materials are also called solid water, because in the end what you get is a solid material that behaves like water, because it only carries compressed spherical compression, like water. Water only carries spherical compression. All the other loadings, if you exclude viscosity, if you assume zero viscosity, with respect to all the other loadings, water will offer zero stiffness, theoretically, if it is if you neglect viscosity. So our idea was to apply such mechanism, such similar mechanism, for designing innovative seismic isolation devices. So what was our idea? Our idea was to confine layers of pentamode lattices between stiffening plates. So if now, what happens if we have a pentamode lattice, either half a cell or one full cubic cell, and we layer those, for example, this is 1/2 of a cubic unit cell of a lattice structure. If you take 1/2 of this over the thickness of this unit cell, and you layer this SFCC, which is FCC is for phase cubic centered unit cell. This is the standard pentamode unit cell. If you take 1/2 of this and you layer such structures obtained replicated horizontally in the horizontal plane, this SFCC unit cell, and vertically you alternate those lattices, those SFCC lattices with stiffening plates, what do you get? And in doing this, we used some additive manufacturing techniques, and we built titanium alloy exemplaries, and those were basically obtained by replicating, by changing the aspect ratio of the lattice and inserted between stiffening plates. So We studied the problem analytically from the manufacturing point of sight and experimentally. And we obtained several results, a series of results about the effectiveness of such structures as vibration isolators. Obviously, when you use such arrangements, such designs, you have to rely on the bending stiffness of the nodes. Otherwise, this structure will collapse to the ground. It will fail. So it doesn't fail only because there is some bending, some non-zero stiffness of the nodes, because it's practically impossible to build zero dimension nodes. So you will always have a rigidity of the node that will change, will modify the response of the structure, so it's not a perfect pentamode structure. And so those structures are, while the first one that you have seen in this movie, this is the one that we have seen. Sometimes it works, sometimes it doesn't. Anyway, there was so this is 1/2, but this was done without 3D printing, with hinges, and so there were other issues. So those are FCC samples, while SFCC are the ones that are obtained by replicating 1/2 of the unit cell in the horizontal plane and adding stiffening plates over the vertical axis. And we have tested at the University of California, San Diego as a candidate isolators, and we have done also some run some computational simulations of the response obtained by adding more and more layers. And this was an introduction. Now I go into some details, but not very much. I just want to give you the main ideas of the main points of our idea. So if you have if you focus on this arrangement, so 1/2 of the FCC pentamode unit cell, and what happens if you add stiffening plates? So what happens in this case? This is the standard case. This is our redesign of the pentamode lattice. So we studied the problem of a repetitive unit, which is formed by 4 rods attached to a central node and connected at the extremities to 2 infinitely rigid plates. Okay? So what we did was to study the kinematics and the statics of this structure to see how it behaves. This is this could be also an exercise, because this is just a structure in the space, very simple. But let's go through some details. So how do you enter the fact that the plates are rigid? You allow only the deformation that you apply to this structure are limited to the modes which contemplate rigid relative movements of the terminal plates. Since the plates are assumed to behave as rigid bodies, we studied the response of this system to relative rigid movements, or the possible relative rigid movements of the terminal plates. Okay? You can have sliding relative movements, you can have vertical relative movements, you can have bending relative movements, and you can have also twisting relative. And you can study the response of this unit to 6 possible relative rigid displacement between the terminal bases. First, we study the statics. And if you, this is simple to show, those are 4 linkages concurring at a node. And assume that the node is unloaded, so it's zero force. So how many equations? I could use the blackboard. No, I'm not saying that I want to. Yes, I could use the blackboard. But anyway, if I use a blackboard, it's very simple to follow. You have how many equations we have? The equilibrium equations. Very simple. At the central node in the 3D space. Yeah, the equilibrium equations impose that. No, this is we don't have bending moments, so we have only forces. We have 3 equations. You do 3 this way, and this is always confused. You do 3 this way. We do 3 this way. It's always 3. It looks like 4 to me. Okay, anyway, it's 3 or 3 as you wish. So you have 4, and also in the United States they do this 4, and we do 3 this way. We use the thumb. Well, you don't use the thumb. Anyway, you have 3 equations and the 4 forces, because there are 4 forces. Okay. The particularity is that the 4 legs are equally oriented in space, are 120 degrees with respect to the central. But you have 3 equations and 4 forces. So what you can do, you can link, you can assume one force as a independent variable, and you can use the 3 equations to relate the 3 other forces to the 4th force. This is what you can do. And this is what we did. And we discovered that those forces are all equal each other. If you impose, if there is no applied force here, and you use the 3 equilibrium equations of the slave rods to link the forces in those rods to the force in the 4th rod, what you discover is that by equilibrium, these forces have to be equal each other. So, by equilibrium in this structure, all the forces have to be the same. This is a simple, we can actually, we could do this example. Do we want to do it? No, do we want to do it with a whiteboard, with blackboard? It's difficult. Oh, you know. Okay. Or no, it's difficult? White, black? Well, yeah, whatever. So this is the result. All the forces are equal each other, independently of what is the loading on the top and the bottom base. This is the equilibrium of the inner node. And you can discard the mass of the lattice, which will be very lightweight, and so assuming that there is 0 force in the inner node, okay? And in this case, this is the result. So now we pass to study the kinematics, keeping in mind that the 4 linkages by equilibrium have to carry equal forces, okay? Now, the kinematics. What we do is this. We divide the elongations. We have always the three slave, the same 3 slave, the road 5-4, this road 5-4 was the master road. So the road that I assume to be the independent, the one with the force assumed as independent variable, axial force. Okay, so this is the master road, and the other 3 are the slaves, in the sense that I can relate the forces in these other 3 roads to the 4th one. So let's call this master and these other 3 slaves, just for understanding, for the ease of understanding. And what I can show with or without blackboard is that these 3 slaves forces are equal to the master force. Okay, let's give this as a result. Let's take this as a result. Now what I do, I study the kinematics. The kinematics consist of relating the elongations of the roads, E, elongations, which means the variation of length, the delta L, the elongations. By elongations, in this case, I mean the variation of length of the roads to the displacements of the nodes. You have a kinematic problems relating the elongations of the roads to the displacement that you give to the nodes. Now, the elongations of the roads are subdivided in 2 sets. We have the elongations of the slaves and the elongation of the master. The master is always the 4th road. Now, we don't need anyone. No, just kidding. The whiteboard is actually the best. Wow. Good. Perfetto. Oops. This is a three struts. But this is more than a pentamode, because we have 2 struts at the bottom and 2 struts at the top. You know, this is more stable than a pentamode. So let me just for a moment forget about this. So there are these 4 linkages, and this is the node 5. Okay, and we verify that this is true, otherwise it will be too much time consuming. We just verify that the 4 forces need to be all equal to each other. Okay, so it's T. So let us sum all these forces and verify that this is true. So what are the cosine directors of the root? So if we take a reference frame, take a reference frame like this, x, y, and z, we can have this one will have as cosine unit vector, will have a unit vector that is 1 alpha, alpha, this is alpha, yeah, one goes in that way, so alpha, 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 alpha is equal to 1 over root of 3, yeah. This other one goes this way, it goes to the front, so has alpha minus alpha alpha. This other one goes this way, goes to minus alpha, alpha, minus alpha, and this other one goes to so I find like this, but this is not possible. I think it's going to be like this. So if you sum the forces in all the directions, what do you obtain? By summing over x, you sum for 1 alpha, 1 alpha, 1 minus alpha, one of these should be minus alpha. Minus alpha is this one, and what is also minus alpha. And also this is minus alpha. So you sum 2 forces alpha and 2 minus alpha, so it's 0. And this is true in any direction. 2 with plus, 2 with minus. So, and since the solution is unique, because you are relating 3 forces to the fourth one with the 3 equations, without the equilibrium equation of the central node, you may be convinced that due to the fact that these are equally oriented in space, the forces need to be equal, need to be the same. So, now just follow this other spec, which is of K forces. Now let's start the kinematics. The kinematics is just the relation between the elongation, the EI dot. If we think of an incremental displacement or velocity, it would be delta Li dot. So, or when you can drop the dot, it means it's an incremental displacement given from the initial configuration. So, delta L is the variation of length. And we want to relate the elongations of the roads to the displacements of the nodes. And what do? We express we get the elongations of the 3 roads. So this is going back. This is 5, 1, 2, 5, 1, 2, 3, and 4. Okay. We take the elongations of 3 roads. These 3 elongations of those are the slaves. Okay, I'm taking this as a master, and this is slave 1, slave 2, slave 3, Y1, slave 1. Oh, what the hell? Slave 2, and slave 4, slave 3, sorry. So my choice was to take as slaves the roads attached to number 1, 2, and 3, and to master the road attached to the 4th node connected to that one. So this is a must, the other 3. So let's partition the elongation, the vector of the elongations of the roads in two subvectors. One collecting the elongations of the slaves. So one collecting the elongations of these roads, and one collecting the 4th is a vector of one unique element, which is the elongation of this other, the 4th road, the master. And let's also partition the displacements of the nodes into subvectors. We partition the elongations into subvectors with the slaves and master, and we also partition the displacement of the nodes into subvectors. So one subvector is the displacement, the displacement components of the central node, and this is D1. The D1 is 1 as a vector, not the displacement of node 1. It's the subvector of D1, which is collects the displacement of node, the central node, and D2 collect the 3 displacement of 1, 2, 3, and 4. So this is a vector with 12 components, and this is a vector with 3 components. Okay? So now, assuming that the roads behave elastically, we can argue that E2 is equal to E1, because if the forces are equal by equilibrium, also the elongations are equal. Okay? This is trivial if the behavior is elastic. So assuming that all the E are equal, E2 and the E1 is equal to E2, you can solve, basically, you can solve D1 as a function of D2. D1 becomes as a function of D2. So you know now what is the displacement of the inner node when you apply prescribed displacements of the boundary. So you know the displacement of all nodes, basically, because you apply yourself the displacement of the bases, and you want to know the displacement of the inner node. And so what we found is that if you apply vertical deformation, this is the solution. If you apply bending deformation, you find, for example, if you apply vertical deformation, if you apply W, supposedly displacement W to the top base, you assume that the bottom base is at rest, because we are studying the displacement of one base with respect to the other. That's what we need. So assuming that the bottom base is at rest. If you apply W displacement to the top base, what you find this way is that the displacement of the inner node has to be Y over W over 2, 1 for the displacement you apply to the top base. This is almost clear, but it's actually hopefully this way. Okay. While and you can also find the displacement that corresponds to 0 elongations. The displacement that corresponds to 0 elongations are shown here. Only these 3 displacements give 0 elongations. So the sliding in one direction, sliding in the x direction, sliding in the y direction, the twisting. This gives zero elongations. So those are solutions without elongations. Why? And this is what we want usually, because in a seismic isolation, what we want that the building is isolated. Not in most cases, you want the building is isolated for shear and twisting motions. Those are the motions of the ground that usually are the most effective. You can have shear or horizontal, and shear waves are also you can have twisting motions if the base of the building is large and the soil is not uniform under the building. So this why in to vertical bending and with respect to vertical bending, so the other three modes, you have one vertical mode and two bending mode, one this way and one this other way, you get some stiffness. You don't get zero elevation. Okay? So this is the result. So we were this is the if you have 2 units for the height, you don't get it. So if you don't have the SFCC, but you have the FCC. So now we have there is all the modes are solved with this one. All the 6 modes will be solved. Obviously, this is without stiffness of the road, assuming zero bending, because this is the theoretical. And so, while if we have the SFCC, the structure that we are studying, you get non-zero stiffness towards in the vertical direction, non-zero, which is what you need. And actually, what we show is a nice result. What we show is that the effective modulus that you get in the vertical direction is, you can express it in this way. V is the solid volume fraction. In lattice material, you usually introduce the solid volume fraction, because you have the unit cell. If you take the ratio between the volume of the solid elements and the ratio of the volume of the unit cell, you have a volume fraction. Volume of solid divided by the volume of the unit cell. This is the volume fraction. And actually, it has been shown that the stiffest lattice material can achieve, and these are the stiffness, the elastic modulus of the effective elastic modulus of the lattice is P/9 E0, where E0 is the Young modulus of the roots. Okay? And obviously, the material was if you have a solid material, it will be the effect will be equal to E0 in naught. Since this is a lattice, this is P/9 E naught. And the interesting result is that it has been shown that the stiffest lattice material can achieve a Young modulus of P/6 E naught. So our material is considerably stiff, as a considerably high stiffness. So it's really a good candidate to be a seismic isolator because it has considerably high vertical stiffness and considerably low, theoretically zero, horizontal stiffness. It has also some stiffness, it opposes stiffness to vertical relative motions, and it opposes stiffness also to bending motions. This is what you want also, because otherwise the structure will collapse under vertical loadings. You don't want that, you know? So there can be bending moments due to the non-uniform loads in the building. So this was actually a metamaterial good for seismic applications. And this is what we published recently, and we did some simulations, numerical simulation with some software in large displacements. And we built, we accounted for the bending of the nodes with the equivalent of Ludhiana. We ran simulations, now you can run simulations of the bending modes, whatever, accounting for non-zero stiffness of the nodes. You have FEM model with accounting for all the effects, also for bend effects. And you can basically, in this case, we accounted for we predicted the ratio between the elastic modulus, compression, and the shear modulus. That is not zero in this case. But always, this ratio is it tends to be high, and it grows by increasing the number of layers, like in common seismic isolators. And so this was, and then we built this physical models of 3D printing, and we ran some tests for different geometries, and we observed quite good comparison between theory and experiments, and we observed also some dissipation properties. In this case, the dissipation, this is also a good dissipative system, because you have several sources of dissipation. What are the sources of dissipation? Friction at the nodes. Friction at the nodes. You have also plasticity of the members. The members, when unlike displacement, go plastic. So you can dissipate energy with plastic friction. So we have proposed this as a seismic result. We have patented this application, which was our idea. And also in this case, 3D printing was essential, because how can you produce this? In the end, we produced also a model with if you have a massive model, massive structure, you can use to usual techniques like this one. But if you want to go with a if you want to go low scale, you need 3D printing, and also it could be also a good technology for manufacturing of these materials, like in the case of the fractal fibers. Also those materials originate their properties essentially on the geometry, because zero shear modulus comes from the geometry. The compression modulus comes from the material. But and you can use this, you can build such a system out of any material. What you need is just a good 3D printer. So you don't need the common seismic isolator nowadays available, require quite advanced technology. So the that's why they are not so much used worldwide. While these technologies systems can be manufactured also through more cheap manufacturing technology as compared to the ones used for common systems. Okay, then this was the real around exercise. And another exercise for you would be that there's no free the cost. Okay, and so we have proposed this also for seismic isolator, but also for helmets, for protecting, you know, in helmets for motorbike drivers. I noticed that you don't use much helmets here, which is the same as in Italy, exactly the same. We look like brother in some sense, we do the same things. But if you need to use an helmet, most injuries are related to the shear motion of the most dangerous injuries. So if you put one of these lattices without a micro lattice within a helmet, you can isolate from shear impacts the head from the helmet. And this is another application. Okay, I'm done. Thank you.
So we can have a little coffee break and then we can
also, you use more tea. In Italy, life is a coffee break. There is always a good reason for having a coffee break. So I am always ready.